So here it states that the sun is a star, and then we're asked which galaxy the sun is in, and then we've got to tick one box which we're going to give as our answer. So initially here I'm thinking about the sun and how the Earth and all of the other planets in our solar system revolve around the sun. So in effect, by asking what galaxy the sun is in, it's also asking what galaxy the Earth and all the other planets are in, which may make it easier for us to answer this question if we didn't know that in the first place. So this is also what galaxy is the Earth in. So hopefully this is just kind of a piece of general knowledge that you probably know from outside of the physics course anyway, but the answer here is going to be the Milky Way. You could probably work this out by deduction if you weren't 100% sure, as all of the other answers are quite different and maybe not what you'd expect it to be anyway. Sometimes it helps me just to think of the Milky Way chocolate bar and its packaging, kind of space related, just to help link back to the idea of space and our galaxy in this question. So then in this part of the question, we're given a table which gives us information about some of the planets in our solar system. The planets are in order of increasing distance from the sun. So when it comes to a question like this, I like to make sense of the table before I get into the main chunk of the question and just understand what it's showing us and what it might be asking. So as you can see in this column here, we've got the list of planets. So Mercury, Venus, Earth. We can see that these are increasing in distance from the sun, just like it said up here in the original question. So then in this column to the right, we've got the time to orbit the sun in years that each of these corresponding planets takes. So Mercury takes 0.2 years to orbit the sun, basically. So now that we've made sense of the table and understand what it's showing us, we can use the information to apply to the later questions. So, there are some planets in our solar system missing from table 1. How many planets are missing? So this is a 1 mark question. It's just looking for us to state the number of planets that aren't in the table, basically. So we could do this in a couple of ways. You might know that there are 8 planets in total in our solar system. So that's an important fact that will come up very useful here. So we could see that there are 5 planets in the table: Mercury, Venus, Earth, Mars and Jupiter. And if we take the 8 that we know there are, minus the 5 in the table, we're given 3 planets that must be missing. Alternatively, we could go about this using one of the phrases I like to remember. So I use the phrase, "My very easy method just speeds up names," just to remember the planets in their order. And through this, I could either count them and work out that there are 8 different planets, or I could work out which ones they are. So my very easy method just speeds up names. So the last 3 missing are Saturn, Neptune and Uranus. And then, obviously, there's 3 of those, so the answer would still be 3. Either way we go about doing it, the question. Now, in this part of the question, we're asked to estimate how many years it takes Mars to orbit the Sun. Now, the key word here is the estimate, and it's showing that we don't need an exact answer. We don't need to use the numbers to do any kind of calculation. This can also be seen, the question's only worth 1 mark. So it's not going to be some kind of complicated calculation. We are just looking for an educated guess in this sort of question. So when it's asking us to estimate and there's a table involved, I'm always going to be looking for trends in the table and looking for ways that I can fill the gap. So we're looking to fill this gap here. So if you look down this column, we can see that the time taken to orbit the sun is increasing. So it starts at 0.2 up to 0.6 and it's continuously increasing between the planets. So we'd expect this trend to continue between Earth and Mars and then again between Mars and Jupiter. So that basically tells us that the time taken for Mars to orbit the sun in years is going to be somewhere in between the times taken for Earth and Jupiter to orbit the sun. So that takes us somewhere between 1 and then 12 years to orbit the sun. So any answer within this given range is going to be correct. We're going to get the mark for. There's no real way of knowing, there's no real way of estimating what the distance between, what the time taken is going to be. So we can just go anywhere between the range. I'd probably go somewhere in the middle, but really anywhere works. I'm just going to put an answer of 5 but we could have gone anywhere between 1.1 and whatever. It's still between the two and following the trend. So now in this final part of the question, we're asked to calculate how many times Venus will orbit the Sun in 9 years. So if I just go back up to the table, we can see that Venus takes 0.6 years to orbit the Sun. So I can just write that down in the information here. Venus takes 0.6 years to orbit the Sun once. So we can put together a sort of a kind of formula here to work out how many times Venus is going to orbit the Sun in 9 years. So if it takes 0.6 years to orbit the Sun once, how many times is it going to take to orbit? How many times is it going to orbit it in 9 years? So we can basically work this out by taking the 9 years and then dividing it by the 0.6 years that it takes to orbit the Sun once. So how many 0.6s will go into the 9, and then that's going to give us the number of times that Venus can orbit the Sun in the 9 years if it takes 0.6 years each time to orbit the Sun. So we can do 9 divided by 0.6, and that's going to give us a round answer of 15 times. So I can just put that in the box there, and then that's that question finished. So in this question, we're given figure 1, which shows how a concave lens forms an image of an object. So in these types of questions, I just like to take a minute to get my head around what's happening in the diagram, so just to understand exactly what everything's doing and why everything's there. So over here we have this arrow, which represents the object itself. And then the smaller arrow here is the image. And then obviously we've got the concave lens along here, which is going to prove very important later on in the question. So I've obviously got it highlighted at the top that it is the concave lens. And then this line along here is the axis as it intercepts the concave lens at its centre. So I'm just going to note on the fact that this is the axis here, just because that will also probably prove useful later in the question. So it's important here to note that we have got the concave lens. So concave lenses are thicker at the edges than they are at the centre. So look a bit like this. So this sort of shape. Obviously we've got the thicker lens at the edges and then the thinner part at the centre. And this means that they cause light rays to diverge or spread out. So we can see this by this light ray here being diffracted after it passes through the lens. This light ray, however, hits the lens exactly at the point where it meets the axis. So the lens meets the axis at the point D. So this ray isn't refracted and it just carries on through the lens in a straight line. So now I'm going to go on to read the first part of the question. So which point on figure 1 marks the position of the principal focus of the lens? So we're looking to find the principal focus of the lens. So the principal focus of a concave or diverging lens is defined as the point on the axis, which is this line here, which we've already labelled up. The point on the axis where the rays hitting the lens parallel to the axis, so this ray here, which is parallel to the axis, is the point where they appear to come from. So if we trace this diffracted ray here back along this dotted line to the point where it meets the axis, we're going to get to point B. So that is going to be our principal focus and the answer to the question. So it's probably quite useful to remember here that the principal focus is the point at which the light appears to be coming from, but isn't the actual point where the light rays are focused by a concave lens. So then in this part of the question, we're asked which 2 words describe the image. So it's important here to make sure we tick 2 boxes so we get both of the marks, and then just to remember that we're talking about the image as opposed to the object. It's quite easy to get confused between the two. So An image is the point at which all the light rays from a certain point on an object, so we're using this point here at the top of the object, the point at which these light rays appear to come together. So we can see that these light rays from the object appear to come together at this point here where the image is. So if we trace this one back down here to where it meets this light ray, they're going to meet here where the image is. As I explained in the previous part of the question, by tracing these lines back behind the concave lens, we've found the point where the rays appear to come together, and then appear is the key word here. So the light rays don't actually come from this point, the image only seems to be there. So this means that we have a virtual image, as opposed to a real image, which would be the case if the light rays actually came together at the place where the image seems to be. This would form an actual image that could be captured on a screen, but that's not the case for what we've got here. So we know that the image is not real. We can easily see by the size of the arrow that it's not enlarged. So the arrow for the object is greater than the arrow for the image. So it's definitely not larger than the object. In fact, it's smaller, so it's been diminished. We can also see that the image is the same way round. It's not been inverted. It's on the same side of the lens. So the final option, which is going to be the correct one, is that it is upright. The orientation of the image has not been changed. The arrows are both pointing in the same direction. So the image is upright. So we can tick the two answers here, which are that the image is upright and it is also virtual. So in this part of the question, we're asked to calculate the magnification produced by the lens. And then we're given an equation here to use, which is the magnification is equal to the image height over the object height. So there's a couple of different ways you can go about doing this. You could either measure them with a ruler, get the measurements for the image height and the object height in millimetres or centimetres, and then work it out like that. Or the way that I'm going to do it is just count the squares, count how many squares tall the image is and how many squares tall the object is, and then calculate it that way. As it's a ratio, it's going to work either of these ways. So I have the object here, and then I can count the squares. So we've got 10 squares in this big box and then an extra 2 on top. So the object is going to be 12 squares high. And then for the image, we've got half of a big square, so that's going to be 5 squares high. Just an easy way of working that out there. So then with that information, I can go back to this part, and then I have that the magnification of the object is equal to the image height, which we had as 5 squares, over the object height, which we had as 12 squares. And that is going to give us an answer of 0.416 reoccurring. And then that rounds to a nice value of 0.4, which I'm going to give as the answer. Now, if you'd have done this by measuring them with a ruler, you would have got about 9.5 millimetres for the image height and then about 24 millimetres for the object height. And so when you do 9.5 divided by 24, you're going to also get an answer that rounds to 0.4. So anything that rounds to 0.4 is going to get you the answer here. You don't need to specify any units. There's no real units that we're working with. It's just kind of a ratio between the image and the object height. But yeah, that's how we get to the answer of a magnification of 0.4. So now in this part of the question, I'm asked to complete the sentence, and I'm asked to choose my answer from the box below. So we've got either decrease, increase, or not change. And then the sentence is, as the object is moved further away from the lens, the size of the image will. So it's going to either decrease, increase, or not change. So I'd probably go about this by drawing out a quick diagram, a quick sketch, and just trying to work out exactly what's going to happen. So if I draw the lens, so this is the concave lens, and then we have the axis along this point, and then I'm going to draw the object. There's an arrow here, and then the ray that goes straight through the point where the axis and the lens meet there, and then another ray parallel to the axis. Then this one will diverge over this way, and then where this one comes back to meet the other ray, we have the image at this point here. So this is the image, and this one is the object. And then if I go in with a different colour and we move the object further away to make sure it's the same height, now we can go back and draw another line through this point where the two meet, this ray. The parallel ray is going to be the same, it's just going to carry on in the direction that it was before. So we can trace this dotted line back yet again to this point here where the image meets. It's a bit difficult to see, but the image is going to be here. And you can see that this image, the arrow, the black arrow here, which is the image when the object is further away from the lens here, is shorter than this arrow here when the object's closer to the lens. So when you move the object further away from the lens, the size of the image is going to decrease. It's an easy way to kind of see what's going on, just using a little diagram, a quick sketch, to kind of figure out what's going to happen when you do what it asks in the question. So in this question here, we're given figure 2, which shows a ripple tank that a student used to investigate water waves. And then below we've got the figure, so it's always a good idea to make sense of it, see exactly what it's showing us, just so we understand the diagram before we carry on with the main part of the question. So basically the whole thing here is the ripple tank, and then this shaded region along here is the water in the ripple tank. And then we have the motor over here, which is clamped to the ripple tank with the bar attached to the motor. So the motor drives the bar up and down, and then every time the bar hits the water surface, it's going to create a wave. So then these waves are basically shown by these lines, which basically represent the peak of each wave. So we've got waves moving this way along the ripple tank. When the bar moves up and down, vibrates and creates more waves. So now that we've made sense of the diagram and understand what's going on there, we can just move on and carry on reading the question. So the student adjusted the speed of the motor so that the bar hit the water more times each second. What happens to the frequency of the waves produced? So if the bar is hitting the water more times each second, it's basically creating more waves each second, because every time it hits the water, it makes a wave. And then we're probably thinking here that frequency is basically the number of waves that are produced each second. And we probably know that because the unit of frequency is hertz. And the unit of hertz is the same thing as saying per second, or 1 over the second. So the number of waves per second is defined as the frequency. So if the bar's hitting the water more times per second, creating more waves each second, the frequency is going to be greater. So the answer to the question, what happened to the frequency of the waves produced, is it's going to have increased. Now, in this part of the question, we're asked to describe how the frequency of the water waves in the ripple tank can be measured. So now, this is linking back to the previous part of the question that I just answered. So the frequency is basically defined as the number of waves produced each second. Alternatively, this could be described as the number of waves to pass a set point each second, because the number of waves are going to be the same when they're generated, and when they pass this point. So if we choose the point along the side of the ripple tank, we can then record the number of waves to pass each second. Now, you're probably thinking that a second's quite a short amount of time to be able to count a reliable and accurate number of waves that pass the point. So if we record the number of waves to pass a point in a greater number of seconds, so maybe 10 seconds or greater, then we can divide this down by the number of seconds that we've counted for to find the number of waves that would have passed in 1 second. This just gives us a better read and it's a bit easier to work with in the experiment. So we're going to count the number of waves to pass a fixed point in a given amount of time here. And then we're going to divide this by the total time taken, which we'll measure in seconds, to work out how many waves pass the point in 1 second as opposed to the total amount of time that we measured. So now in the final part of the question, we are told that the student measured the frequency of the water waves as 5 Hz. And then we're asked to calculate the period of the water waves. And then below this, we're given the equation period equals 1 over frequency. And then we're asked to choose the unit from those in the box. So we have the meters, we've got meters per second, and then we've got seconds. So I've spoken quite a lot about frequency throughout this question and how it's the number of waves to pass a certain point every second. So we've already said that the unit is hertz, as we can see up here. And then that's the same as per second, which we can write as seconds to the -1, or that's equivalent to 1 over seconds. So those are the units for frequency. They're all equivalent to the hertz. So we're going to use those later on to work out the units for the period. So if we go ahead and find a value for the period, we can use the equation. So the period is equal to 1 over the frequency, and then we're obviously given the frequency up here, which we've got as 5 Hz. So 1 over 5 is going to give us an answer of 0.2. So I can put this down here, the value is 0.2. And now we've just got to work out the units. So if I go back up to the equation, we have the units for frequency, and a good way to use these in this sense is going to be as 1 over seconds, the units for frequency. The 1 at the top here doesn't have any units, it's just a value. So to find the units for period, we're going to do the 1 divided by the units for frequency, which is 1 over second. And then this is the same as multiplying it by the reciprocal. So 1 multiplied by the reciprocal of 1 over seconds, which is just seconds. So the units for the period are 1 multiplied by seconds. So we're just left with seconds as the unit. So then we can go down here and write that in as the unit. Another way of kind of working this out would be looking at the equation, and we're working with 1, which doesn't have any units, and then we're working with frequency, which is working with seconds, just seconds. They might be in a different form, it might be per second, but there's no real reference to meters in the equation. We're not working with any values which are measured in meters, so this probably leads to the fact that the period is just going to be measured in seconds, no meters are involved, and that just leaves us with the answer of seconds alone because the other two do have meters in them. So in this question, we're given figure 3, which shows 2 paper clips hanging from a bar magnet, and then it's a good idea just to make sense of the figure. So we've got the permanent bar magnet here, with the North Pole on the left-hand side and then the South Pole over to the right-hand side. And then we've got the 2 paper clips hanging from the South Pole of the magnet being attracted here, and then the 2 paper clips are attracted to one another here. So then we're given that the paper clips have become magnetised. So although the main bar magnet is a permanent magnet, the paper clips aren't permanent. They're going to be temporary magnets. So they're going to have induced magnetism when they come within the range of the magnetic field of the bar magnet. So paper clips on their own don't produce a magnetic field all of the time. And then we're asked to label the north and south poles of both paper clips. So initially here we're working with magnets, we're working with a permanent magnet and attraction. So I'm instantly thinking that a key piece of information I'm going to be working with is that opposite poles attract one another. So the paper clips in this case have to be induced magnets, meaning that when they enter the magnetic field of the permanent magnet here, the bar magnet, the south pole of the magnet will induce a north pole at the top of the paper clip. So we can write that down here. We've got the N for north pole at the top of this paper clip. This will then be attracted back to the magnet as opposite poles attract. So we've got the south pole and the north pole attracting here, which is what keeps this paperclip attached to the magnet. As this paperclip's now an induced magnet, if the top is the north pole, then the bottom of this paperclip must be its south pole. And then the whole process of magnetic induction is then basically the same between the two paper clips. So go back to the same sort of ideas, we can work out that the top of this second paper clip is going to be a north pole again, because the south and the north are attracting between these 2 points, and opposite poles attract. And that must leave the bottom of this paper clip to be the south pole. So in this part of the question, we're told that a student investigated how the number of turns of wire on an electromagnet affects the strength of the electromagnet. Then we're told that figure 4 shows the equipment used by the student, and that throughout the investigation, the student kept the current through the wire constant. And then below we have figure 4, which is we're going to take a minute to make sense of and just understand exactly what everything's doing in the diagram. So we've got the electromagnet here with the coils of wire, and then we're working out using the experiment to find how the number of turns of wire on the electromagnet is going to affect its strength. So this is what we're going to be changing, the number of coils. And then we have the circuit around here. We've got the power supply here, which is providing the voltage, and a variable resistor so that we can vary the current that's flowing through the circuit to make sure the current stays constant, as it says in the information at the top. And then we've got the ammeter so we can measure the current as well. And then we obviously have this chain of paper clips, which we're going to be adding paper clips to, which is attracted to the electromagnets here. So then we're told that the student measured the strength of the electromagnet by counting the number of paper clips the electromagnet could hold. And we are asked to explain why it was important that the paper clips were all the same size. So we've got the keyword explain here, meaning that we're going to have to give that a bit of extra development to our answer, not just a single point. There's 2 marks here, so we're going to make our point and then explain why. So as we're counting the number of paper clips as opposed to the mass hanging from the magnet, we need to ensure that the paper clips are all of the same mass. Having one paper clip of a greater mass, for example, would be like having 1 and a bit of the correct size paper clips. So the number of paper clips we counted the magnet to be able to hold is actually less than the number of the same size paper clips that it can actually hold. So it's a variable that must be controlled in order to ensure that it's a fair test and experiment, and this is so that we can then directly compare our results for the number of paper clips the electromagnet can hold at each different number of turns, which is the point of this experiment. If the paper clips were all of different sizes, we wouldn't be able to reliably compare the numbers that they can hold because they're all of different masses, so we don't actually know the mass, total mass that it could hold, which relates to the number of the correct size paper clips. So now we're given table 2, which shows the students' results. So in the left-hand column here, we have the number of turns of wire on the electromagnet. So that's the variable that we're changing to work out how this relates to the number of paper clips that can be held. That's kind of the main aim of the experiment. So these are the results here. And as we can see, they're increasing by 10 each time as we go down the column. And then in the right-hand column, we've got the number of paper clips held, which you can see also follow a pattern, and they're increasing as the number of turns on the wire gets bigger. So then we're asked to describe the pattern shown in table 2, and then this question's worth 2 marks. So we're going to kind of describe the relationship and then go on to give a little bit more detail about the nature of the relationship just to get that second mark here. So the first mark is for kind of pointing out the obvious, and we're saying that as the number of turns of wire on the electromagnet increases, so does the number of paper clips held by the electromagnet. So these two, when one increases, the other increases. And then just to go a little bit further and get that second mark, we can see that when for every increase in 10 of the number of turns, we have an increase in 3 for the number of paper clips held. So this shows a linear pattern in the data and shows that the number of turns is directly proportional to the number of paper clips held. So you could either say that there's a linear pattern between the two and as one increases the other does, or you could just say the two are directly proportional, and that would gain you both marks alone just for saying that they're directly proportional. So now in this part of the question, we're told that the student then used 50 turns of wire on the electromagnet, and that the electromagnet picked up 18 paper clips, and this was more paper clips than the student had expected. So the key word here is more, and we're going to come back to that later on just to see how important it is. So then we're asked which one is the most likely cause of this result, and then to tick one of the below boxes. So I'm just going to read through the boxes, read through the options, and see which one is the one that would cause more paper clips than anticipated to be picked up, and then whether the other two would cause less or maybe have no effect on the number of paper clips. So firstly, we have that the paper clips used with the 50 turns were larger than the others. So we've discussed this idea in the previous parts of the question. If the paper clips are larger, the electromagnet isn't going to be able to pick up as many because we've got larger paper clips than we'd anticipated. So this would actually have the adverse effect, so it would cause less paper clips than the student had expected to be picked up, so it can't be this first box. So now we can move on to the second one. We have that there were less than 50 turns of wire on the electromagnet. So we know that if there were less than 50 turns, then there's going to be a weaker magnetic field around the electromagnet, so less paper clips are going to be able to be picked up. We could always refer back to the table in the previous part of the question, so we'd see that with less turns on the turns of wire on the electromagnet, less paper clips can be picked up. We could use the values in that table to see this again for ourselves. So now that we've discarded these two options, we're hoping that it's going to be the last one, because by process of elimination it should be. So we have here that some of the paper clips were already magnetised. Now if some of the paper clips are already magnetised, it's going to be easier for them to be held by the electromagnet, so this is going to cause more paper clips to be able to be held by the electromagnet, which is what the question was asking. So this is the correct answer, and we can tick the box next to it. So now in this part of the question, we're told that the student repeated the measurement for 50 turns of wire 3 more times, and this gave her the following set of results. So we have 18, 16, 14 and 15. And then we're asked to explain what the student should now do with the 4 results for the 50 turns of wire. So it's useful to note here that the question is worth 3 marks, so we're going to be looking for quite a detailed explanation with a couple of points just backing up what we're doing. So initially here I'm looking at the results and I'm thinking that we have the 18 over here which is quite a bit greater than the other. So we've got 18, which is 4 greater than 14, whereas we have the 16, 14 and 15, which are all within 2 of each other. So in this case, I'm going to take the 18 and discard it as an anomaly. So I'm discarding the result of 18 as an anomaly in this case. So then we have the 3 new results, which are the 16, 14 and 15. And we need to just justify why we can discard 18 as the anomaly and why we can keep these 3 to then find the average of. So we can do this because 16, 14 and 15 are quite similar to each other. They're within 14 and 16 have a difference of 2 and the others have a difference of 1. So the numbers are really similar. And that's enough justification as to why we're going to keep those and discard the 18, which is quite greater than the rest of them. So then we can take our results to this and we can find the mean of these, which is going to give us an answer of 15 as the mean of those 3 results. So that is what she's going to do to work out the more reliable result, which has taken into account a few different repeats and given us the answer of 15. So now in the final part of the question, we're told that the student wrote the hypothesis, increasing the current through the wire will make the electromagnet stronger. And then we're asked to describe how the student should change the investigation to test this hypothesis, as opposed to the original one that we were testing, which was to do with the number of turns of wire on the electromagnet. So then this part of the question is worth 3 marks, so we're going to be stating 3 main things that the student should change to test this hypothesis instead. So firstly, I'm thinking about what we're going to be measuring this time and what we're going to be controlling this time instead. So this is going to change from the original experiment. So if we look back to the original experiment, we were changing the number of turns on the wire to see what effect this had. Now in this experiment, we're going to want to control the number of turns and keep it the same, as this is no longer going to be the independent variable that we're changing throughout the experiment. So we need to keep the number of turns constant here. However, our new independent variable, the thing that we're going to be changing throughout the experiment, is going to be the current in the circuit. And the circuit diagram has a variable resistor drawn into it, so we're basically going to use the variable resistor to change the current a few times just to really work out how we're going to go about this. So then when we change the current, each time here we're going to do the same as we did last time and count the number of paper clips that the electromagnet will hold at each different value of current. So that's the one thing that's going to stay the same from the previous experiment. We are still going to be counting the number of paper clips, but we are going to change the control variable and then the independent variable, which we've just spoken about. So to get each of the marks, you're going to get the first mark saying that we're keeping the number of turns constant. That's our new control variable. Then the second mark is going to be for stating the new independent variable, so we're changing the current. And then the third mark is going to be for stating the dependent variable, so what we're measuring, and that's stayed the same from the previous experiment, so we're measuring the number of paper clips that the electromagnet can hold. So for the first part of this question, we're told that some objects are transparent and some objects are opaque. And then we're asked which one of the objects in figure 5 is transparent, and we are asked to tick one box. So it's a good idea here just to work out exactly what transparent means, make sure we're confident with the definition. So to put it in simpler terms, transparent basically means that the object is see-through. So transparent objects transmit light. So not all of the light that hits the surface of this object is absorbed or reflected. Most of the light for transparent objects can pass through the object to the other side. So then if we look at the objects that we're given, we've got a book, a pencil rubber, a glass vase, and a ceramic mug. Now, it should be quite easy to see here that the book, the pencil rubber, and the ceramic mug, light is not going to pass through any of these 3 things. However, the glass vase, it definitely will pass through. It's see-through, it's glass, the light will pass through and get to the other side. So for that reason, the glass vase is the object that is transparent here. So now for this part of the question, we're asked to complete the sentence by choosing an answer from the box. So we've got the word absorb, reflect or transmit. And the sentence is an opaque object does not do something to light. So we've just been dealing with transparent objects and we know that they're see-through, they transmit light. Now opaque is going to be the opposite to transparent. So opaque objects are objects that do not transmit light. So when visible light waves hit opaque objects, they absorb some wavelengths and they're going to reflect some wavelengths, but they are not going to transmit any light. So by filling in the answer here, we've got an opaque object does not, and then we've just figured that out, that the answer is transmit light because they do absorb and reflect light, but the light cannot get through them. So now we're told that a student wears a white t-shirt and a red baseball cap to a party, and we're asked, why does the t-shirt look white in white light? So, opaque objects are, the colour of opaque objects depends on which wavelengths of light they reflect. So, for a white object, the white object is going to reflect all of the wavelengths of visible light for it to appear white, and it's going to reflect all of these wavelengths equally. So when all of the wavelengths of visible light mix together, we're going to get this white light, and that's going to be why the t-shirt looks white. So to get the mark here, we're just going to say that the t-shirt reflects all the wavelengths or all of the colours of visible light, and that this happens equally. And that's going to gain us this mark. So now we're asked to explain how the colour of the baseball cap appears to change when the room lights at the party change from white to start with to blue. So here we're asked to explain the reasoning behind it, and the question's worth 2 marks. So we're going to state what happens to the colour of the baseball cap, and then we're going to go on to explain why, just to gain us that 2nd mark. So firstly, in the presence of white light, the baseball cap is going to appear red. So an opaque object's colour depends on which wavelengths of light are reflected by the object. So when visible light shone on the cap, it's going to reflect the red wavelengths of light because it's a red object and absorb all of the other wavelengths, so it's going to appear red. Now, when the light is changed to blue, however, this is going to have a different outcome as the cap's not going to reflect any of the blue light. There's no other wavelengths of light for it to reflect, so it's going to appear black. It's going to absorb all of this blue light. There's going to be an absence of wavelengths of visible light that are reflected, so it's just going to appear black. And basically that's how we get the 2 marks. So the first one for saying that it changes from the red to the black, and then the second one for either saying because the cap absorbs all of the blue light, or by saying that the cap does not reflect any of the blue light. And now in this question, we're told that a student investigated how the type of surface affects the amount of infrared radiation that the surface absorbs. So then we've got figure 6, which shows the equipment that the student used. So we've got the infrared heater in the centre, which is going to emit infrared radiation. So it's going to travel in both directions towards the surfaces. Then we have a shiny silver surface on this side, which is the metal sheet. And then over this side, we've got a matte black surface, which is on a metal sheet. And then we've got wax here, which is holding on a drawing pin. So then we're told that the metal sheets absorb infrared radiation and that the wax melts and the drawing pin falls off the surfaces. So in the investigation, there are several variables which we'd expect in an experiment, and we're asked to draw one line from each variable to the correct description of that variable. So here I'm just going to start by noting down exactly what each variable means, just so we're 100% confident with what the control variable, dependent and independent variables are. So for the control variable, we're basically working with what we're going to keep the same throughout the experiment. Which one of these descriptions are we not going to change, and we're going to make sure we keep the same in order for it to be a fair test. Then we've got the dependent variable here, which is what we're going to measure. So why are we doing this experiment? What results are we looking to get from it? What are we measuring throughout the experiment? And then we've got the independent variable, which is the one thing that we're going to change throughout the experiment in order to get this range of results and to see what the outcome of our research and experiment is. So in this case, the control variable is going to be the distance from the metal sheets to the infrared heater. So they've both got to be the same distance away from the heater in order for this to be a fair test, because as the distance between the two increases, the intensity of the infrared photons are going to decrease. This means less energy is going to be provided to the surface every second, and this is an important factor in the experiment. So we've got to make sure that they're receiving the same number of photons per second, so that they're the same distance away from the heater. Now moving on, we have the dependent variable, which, if it's what we're measuring in this case, it has to be the time taken for the drawing pin to fall off. So this is the variable that we're going to be measuring as we change the final variable that we have as the independent variable. So we're looking to change the surface colour of the metal sheets. So we can see that quite easily in the diagram, because we've already got one that's silver and then a matte black one. So we've got two different sheets here, and that's basically what we're going to be changing in order to see how the colour of the sheets affects the time taken for the pins to fall off. So how this independent variable is going to affect the dependent variable when we're controlling the control variable, which is the distance. And now we're asked what the main hazard is in this investigation. So initially here I'm thinking that we're working with an infrared heater. So infrared heater is giving off infrared radiation, which can be damaging to your eyes if you have prolonged exposure to the infrared radiation. Also, infrared waves travel through the air, and then when they touch the surface, they're going to release heat energy. So this could prove a problem also. So we just need to be careful around the infrared heater. So I'm going to describe that as the main hazard in this experiment. So for the final part of the question, we're told that the drawing pin attached to the matte black metal sheet fell off first. And we're asked what can be concluded from this result. So here we're basically looking to round up the results of the experiment and give this final conclusion on what's happened and what these results show. So in order for the drawing pin to fall off, it basically means that the wax has had to melt, and in order for the wax to melt, it means it needs to have gotten hot, and this heat is going to come from the infrared radiation, which is heating up the metal surfaces. So if the pin on the matte black surface has fallen off first, this surface must have gotten hotter more quickly in order for the wax to melt and it to fall off. So for it to have gotten hotter more quickly, the matte black surface in this instance has got to be a better absorber of the infrared radiation than the shiny silver surface on the other side, for which the drawing pin hasn't fallen off because it hasn't absorbed enough of the infrared radiation to heat up enough to melt the wax. So we just have to make sure in this question that we're given a comparison between the two surfaces just to gain that mark. So I'm just going to say that the matte black surface is a better absorber of the infrared radiation, and that's a good conclusion to come to from the result that we've been given. So in this question we have figure 7, which shows 4 blocks of different materials which are floating on water, and that the 4 blocks are all of the same volume. So then we have figure 7, which shows us the water surface, which is the light grey shaded region, and then we have the 4 blocks. So A is mostly sitting below the water surface, B sitting half above and half below, C is sitting mostly above the water surface in this region here, and then D is sitting mostly below the surface. And then we're asked to use this information to answer the question, which of the blocks has the smallest weight? So initially here I've noticed that we're told the volume of all the blocks are the same. And then the question here also references the weight of the blocks, which could be converted into their masses. So I'm initially thinking that the equation density equals mass divided by volume, or P equals m over v. But this equation is going to come in quite useful here. So if we're looking for a block with the smallest mass, so a low mass here, it's the same as looking for a block with a low density. Now this is because the density is proportional to the mass, as we can see in this equation here. So the block with the smallest density is going to be the one that's going to have most of its mass above the water, above the surface of the water. And if we're looking for the block with the lowest density, because it needs to have the lowest mass, then in that case this is going to be C, because most of the mass of C is going to be concentrated above the water surface. Denser objects will sit lower in the water, so less dense objects are going to sit a bit higher in the water and more above the water, so that's C in this instance. So now in this part of the question we have figure 8, which shows a life buoy next to a deep swimming pool. So we have the life buoy on the side of the pool here, and then the pool obviously down here. And then we're told that the life buoy has a mass of 2.5 kilograms and that the gravitational field strength is 9.8 newtons per kilogram. And we are finally asked to calculate the weight of the life buoy by using the equation that weight is equal to mass times gravitational field strength. So this question is worth 2 marks. We're not asked to give a unit. The unit is already displayed down the bottom. That's going to be in newtons. So we just know it's going to be quite a simple, straightforward calculation. We're going to get the answer, and that's going to give us both of the marks here. So by basically subbing in the numbers to the equation that we're given, we're going to find the weight of the life buoy. So we have here that the weight of the life buoy is going to be equal to the mass of the life buoy, which we have as 2.5 kilograms. It's important just to check the units as we go to make sure they're going to be right at the end. And then we're multiplying that by the gravitational field strength, which is 9.8 newtons per kilogram. And we can see here that if we're multiplying the units together, just to check that we were working in the correct units, they're both to do with kilograms, so we think that it's going to work out. But if we have newtons per kilogram, so newtons over kilograms, multiplied by kilograms, this is going to leave us with the units of newtons as the kilograms cancel out, and then that's the unit that we're given at the bottom, so we know that we don't have to convert any of the values we're already given in the question. So then we can simply do the 2.5 multiplied by the 9.8, and that is going to give us 24.5 newtons. It doesn't ask us to round it to any number of significant figures, so we could round it to 25, but I'm just going to give my answer as 24.5 newtons. So now we're told that when thrown into the water, the lifebuoy floats. The two forces acting on the lifebuoy are the weight of the lifebuoy downwards and then the upthrust upwards. And then we're asked, how big is the upthrust on the lifebuoy compared to the weight of the lifebuoy? So here I'll probably find it easy to start with a diagram, just making sure I know exactly what's happening. So if we draw the lifebuoy here, then we have the upthrust, which is going to be acting upwards on the lifebuoy, and then of course we have the weight, which is going to act downwards. So for this object to float on the surface of the water, it needs to be in equilibrium. The forces acting on it need to be in equilibrium. So this basically means that there's no resultant upwards or downwards force for it to stay floating on the surface of the water, there needs to be no resultant force. And if the only two forces acting on the lifebuoy, upwards and downwards, are these two forces, in order for them to cancel out, for there to be no resultant force, the upthrust is going to have to equal the weight, so that there's no resultant upwards or downwards force, the two forces cancel out, so there's a net force of 0. So in this case, we're going to go with the third box and say that the upthrust is going to have to be the same as the weight, so that there is no resultant force. And now I'm asked to write down the equation which links acceleration, mass, and resultant force. So this is just a 1-mark question. We're simply asked to write it down and state the answer. So a good way that I like to remember this one is by using the word fam. So we should probably remember that this equation is Newton's second law, and it's the one that links the acceleration of an object, its mass, and how the resultant force causes this acceleration due to the mass. So I use the word fam, so I know that the force, the resultant force applied on an object, is equal to the mass multiplied by the acceleration. Now if we take the symbols for these, we have F equals ma, and we can just rearrange the A and the M, and that's where we get fam from, which is just an easier way to remember it. So now we're told that a rope is used to pull the lifebuoy to the side of the swimming pool. A resultant force of 4 newtons acts on the lifebuoy. The mass of the lifebuoy is 2.5 kilograms, and we're asked to calculate the acceleration of the lifebuoy. So here I'm noticing that yet again we're going to be working with the resultant force, the mass, and the acceleration of the lifebuoy. So this is bringing us back to the formula that we just used, we just wrote down in the previous question. So we have the formula force is equal to mass times acceleration. Now instead of working out the force this time, we're actually going to be working out the acceleration. So we can substitute in the values that we have. So we have the force and the mass, and then we can use this to work out the acceleration. So the first mark here we're going to get for substituting in these values. So firstly we need the force, which we have as 4 newtons. So we have 4 newtons is equal to the mass, which we have as 2.5 kilograms. And then that's multiplied by the acceleration. So if we rearrange this, divide both sides by 2.5, we're going to give ourselves an answer for the acceleration. So we have the acceleration is equal to 4.0 divided by 2.5, and that gives us a final answer of 1.6, which I can put here. So we get the first mark for basically substituting the values into the formula F equals ma. We're going to get the second mark here for dividing both sides by the 2.5, so having acceleration is equal to 4 divided by 2.5. And then we're going to get the third mark for finally getting the correct answer from this calculation. Alternatively, if you were just to do this in one step, which we wouldn't advise, you should show you're working throughout it all, you would get 3 marks just for stating the answer here too. So in this question, I'm showing figure 9, which shows a forklift truck lifting a heavy crate. So then in figure 9, we have the truck over here, and then we have the crate, which the truck is lifting. The crate weighs 11,500 newtons, and it's lifted vertically by 2.6 meters. So we can see that here the crate, this arrow represents the weight of the crate, the force, which is weight, acting downwards. So we've got that 11,500 newtons, and it's lifted vertically by a distance of 2.6 meters. So that's going to be this distance here, the distance through which it's lifted. So I can draw that on, distance of 2.6 meters. Then we're asked to calculate the work done to lift the crate, and we're given the equation work done equals force times distance. So we are given the force, used to lift the crate here in the question, and we're given the distance through which it's lifted. So we can work this out. So using the equation, we have the work done is equal to the force, which we have here as 11,500 newtons. Multiply that by the distance of 2.6 meters. And that is going to give us an answer of 29,900. And if we multiply the units together, we have the newtons and the meters. So that's going to give us 29,900 newton meters. And we probably know that 1 newton meter is equal to 1 joule. And then the joule is the unit that we've got here. So we can just substitute that in there as 29,900 joules as our final answer. Now we're told that the weight of the crate causes a clockwise moment of 13,800 newton meters about the centre of the front wheel of the forklift truck. The weight of the forklift truck and driver causes an anti-clockwise moment. And we're asked what the minimum size of the anti-clockwise moment needed is so that the forklift truck does not topple over. So in order for this truck not to topple over, it has to at least be in equilibrium. The anti-clockwise moment has to equal the clockwise moment. So for an object to be in equilibrium, we have this law that the clockwise moment needs to equal the anti-clockwise moment, and that is the principle of moments. So in this case, if we have a clockwise moment of 13,800 that we see in the top, in order for this object to be in equilibrium and not topple over, the anti-clockwise moment must be at least 13,800 newton meters, and this is to ensure that the clockwise moment isn't too great, so the forklift won't topple over. So the minimum size of the anti-clockwise moment here is going to be that 13,800 newton meters. And when the anti-clockwise moment is 13,800 newton meters, that means that the object's in equilibrium because the anti-clockwise and clockwise moments are equal. Now, in this part of the question, I'm asked to write down the equation which links distance, force, and the moment of a force. So here, when I'm thinking about these three things, it's instantly reminding me of the work with levers and that kind of thing, those kind of topics. So it's helping me recall the fact that when we have a moment, it's going to be the force times the perpendicular distance. So the moment of this force is the force multiplied by the perpendicular distance. This is 1 mark, so it's just looking for me to basically state that equation. So I can just write it down that the moment of a force is equal to the force, and that's going to be multiplied by the distance. Now, a good way of remembering this, if we assign letters, so we have the moment, which can be represented by a capital M, is equal to the force, which is capital F, multiplied by the distance, lowercase d. We can just rearrange this to M equals dF, and then we have MDF, which is a wood. Just helps me remember this and helps me recall this formula. So we have M equals dF for this question. Now, in this part of the question, we're asked to calculate the distance d, which is marked on figure 9. So that's that distance here. It's between the centre of the front wheel, from which the moments in the previous parts of the question were taken from this point, and it's the distance between that and the centre of the crate, from where the weight of the crate, which is 11,500 newtons, from where that acts. So here we're going to be relying on the previous part of this question and the formula to work out the moment of a force. So we had that the moment of a force is equal to the force multiplied by the distance. So in this case, previously in the question, we're told that the clockwise moment of the weight of the crate about the centre of the front wheel was 13,800 newton meters. We have here that the force is going to be 11,500 newtons, as that's from the crate. The crate has a weight of 11,500 newtons, and that's going to be the force in this instance. So force is equal to 11,500. And then D is what we're going to be calculating in this instance. So if we substitute these back into the formula, we have the moment, which is 13,800, is equal to the force, which is 11,500, multiplied by D. So in this case, the D is going to be 13,800 divided by 11,500. So here I'm just dividing both sides by 11,500. And then that's going to leave us with a distance, which is going to be 1.20. And then that distance is going to be in meters here, because if we go back, we had the moment, which was in Newton meters, over the force, which is in newtons. So the newtons cancel out and leave us with meters. So the answer to this question is 1.20 meters. You're going to get your marks here, firstly for substituting the force and moment into this equation here, and then for rearranging to find D, and then finally for the correct answer here at the end. So in this question, we're given figure 10, which shows the positions of 3 types of wave in the electromagnetic spectrum. So we have figure 10, which goes from radio waves through A, B and C, which are missing, then to ultraviolet, X-rays, and then D. And then we're asked which position shows where visible light is in the spectrum. So we're asked whether that's A, B, C or D, where is visible light going to be? So basically here we're looking to work out the order of the electromagnetic spectrum and then fit in where visible light's going to be. So there's a couple of ways that I like to remember the order of the electromagnetic spectrum. One of them being the electromagnetic spectrum song, which is definitely one of the main things I remember from GCSE Physics. It's very catchy and I would definitely suggest learning it. So it goes from radio waves to microwaves. So microwaves is going to be A. And then for B, we go infrared radiation. C, we have as visible light. Ultraviolet, X-rays, and then the final one is going to be gamma rays. Alternatively, another way of remembering this is using the acronym for the EM spectrum. So, raging Martians invaded Venus using X-ray guns is one of the ways that I like to remember it. So we can just use that to work out that it's going to be radio waves, microwaves, infrared, and then visible light, which is what we're looking for. So visible light is going to be the fourth one, and in this case that is going to correspond to box C. So we can tick that as our answer. So now we're asked which one of the statements about electromagnetic waves is correct here. And we're asked to tick one of the boxes. So we have that radio waves has a higher frequency than X-rays, radio waves have a longer wavelength than ultraviolet, X-rays have a longer wavelength than radio waves, or X-rays travel faster through the air than ultraviolet. So here we're working with the frequency and wavelength of the waves of the EM spectrum. So I think a useful thing to start with here is going to be a quick diagram. So if I start with radio waves over to the left-hand side, and then take gamma rays, which are going to be at the other end of the spectrum, as we worked out in the previous question. Now I'm going to just draw kind of a diagram showing the wavelength and the frequency of the waves. So they start off with a longer wavelength, gradually getting shorter and gaining a higher frequency until you get the gamma rays, which are really high frequency, short wavelength waves. So a way that I remember which way round this is when I'm singing through the electromagnetic spectrum song in my head, I start it off quite slowly and then make it faster and faster as I'm going, get really fast by the time I get to the gamma rays part of the chorus. And then that shows that it's a really short wavelength and a much higher frequency. That's just how it works in my head. So here we can see that the radio waves obviously have a longer wavelength, so I'm going to do an up arrow to represent longer and then a lambda to represent the wavelength, and they have a lower frequency because the waves are less frequent because they have this longer wavelength. And then for the gamma rays, they have a shorter wavelength and a higher frequency in this case. So now I can look down the boxes again and I can see that here in the second box we have that radio waves have a longer wavelength. They've got the highest wavelength out of the electromagnetic spectrum. So they have a longer wavelength than ultraviolet light, which is going to be somewhere around here, just between visible light and X-rays, which is going to be obviously a much shorter wavelength. So we can go ahead and tick the second box here. So now here I'm asked to give one possible danger of exposing your skin to ultraviolet radiation. So initially here I'm thinking that we're working with UV radiation, and I know that the main source of UV radiation on Earth is going to be from the sun. This question is worth 1 mark, so I'm just looking to state one of the possible dangers of exposing the skin to UV radiation, or in this case, exposing your skin to the sun for prolonged periods of time. Now I know that the sun can cause skin damage. It can cause damage to the skin through sunburn and things like that, but one of the main risks is a risk here of skin cancer. So the risk of skin cancer is going to gain us 1 mark for this question, and we're going to get the full marks here. Alternatively, I could write about how it may also cause the premature aging of skin. Alternatively, that would be enough to get the mark for the question. However, I do have to be quite specific in my answer. Just saying a risk of cancer isn't going to be specific enough, and also saying skin damage alone is also not going to be specific enough. So I need to just make sure I really get the exact point across that I'm trying to make just to get that full mark. So now in this question, we're told that having an X-ray exposes a person to ionising radiation. Table 3 gives the average radiation dose for an X-ray of the chest and an X-ray of the upper digestive system. And then we can see that here. So we've got the part of the body in this column. So we have the upper digestive system and then the chest. And then in the right-hand column, we've got the radiation dose in MSV. So for the upper digestive system, it's going to be 5.0. And then for the chest, it's going to be 0.1. So then we're going to be using this information in the main part of the question. So we have that the risk of an X-ray causing cancer is about 1 in 20,000 for each MSV of radiation received. Compare the risk of developing cancer from having an X-ray of the upper digestive system compared with the risk from having an X-ray of the chest. And then obviously we're going to be using this data that we found in Table 3. So in order to compare the two, I'm going to work out the risk of both, and then I can really see a quantitative measure of the risk for each, the chest and the upper digestive system, and then I can compare the two really well and see which one is going to have a greater risk of developing cancer. So in order to do this, I can start with the upper digestive system. Now, the risk per 1 MSV is going to be 1 out of 20,000. Now, for the upper digestive system, we have 5 MSV. So in order to work out the risk here, I'm going to multiply this by 5. And that's going to give me an answer of 1 over 4,000. So 1 in 4,000, that's the risk for the upper digestive system portion of this question. Now I can go on to work out the risk from a chest x-ray. So I'm going to take that 1 over 20,000, which is the risk per 1 MSV. And I'm going to multiply it by 0.1 in this case, because we have 0.1 MSV for the chest in this question. And that's going to give me an answer of 1 over 200,000. So now that we have these two results, we can make a comparison. So for a chest x-ray, we've got 1 over 200,000, and that's a much, much smaller risk than the upper digestive system risk, which is 1 over 4,000. In fact, for the chest x-ray, this is 50 times less likely. The risk is going to be higher for an x-ray of the upper digestive system than the x-ray of the chest, and this is going to be by a factor of 50. So this is a 2-mark question, and I could have gotten both of the marks by just writing down and working out these two calculations here. So just by working with these numbers and working out the risk for both the UDS and the chest x-ray, I would have got both of the marks for this question. Alternatively, I could have just written the bit in purple down the bottom, so I would have got 1 mark for saying that the risk is higher for the UDS x-ray than the chest x-ray, and then the 2nd mark for saying that this was by a factor of 50. So there's a couple of different ways you could go about this. One's a bit more qualitative, and then the top one with the calculations is just working with the numbers and coming out with the exact values of the risk for these ones. So in this question, we're given figure 11, which shows a container filled with water. The 3 holes in the side of the container are sealed with rubber stoppers, and then we're given the figure, so you can see the 3 holes here, here and here, and then the rubber stoppers which are filling them. We're then told that the water exerts a force of 27 newtons on the bottom of the container. So this is a key point where the force has been exerted. And we also have that the cross-sectional area, again, of the bottom of the container is 0.09009 metres squared. And we're asked to calculate the pressure exerted by the water on the bottom of the container by using the equation below, which is pressure is equal to force divided by area. Then we've also got to make sure we choose the unit out of those in the box and put that at the end of the question to get the last mark. So this question's 3 marks. There's going to be 2 marks for the main calculation. So there's going to be 1 mark for substituting in the values, 1 mark for getting the correct final answer, and then the final mark's going to be for getting the correct unit. So I'm going to start off here by using the equation. So we're trying to work out the pressure, and that's going to be the pressure exerted on the bottom of the container by the water. So we need the force that's exerted on the bottom of the container by the water, which we can see in this line here, we have a force of 27 newtons. So I'm going to write that down. I'm going to make sure I include the units just because we need to work out the units at the end. So working with the units throughout is going to help us work out what they need to be at the end of this. And then we're going to divide that by the cross-sectional area, which also needs to be of the bottom of the container because that's where the force is working on. So we have in this line that the cross-sectional area is going to be 0.009 metres squared. So I can just substitute that one in as well. And then we can put this into our calculators, and that's going to give us an answer of 3,000. And then if we work with the units, so we have newtons divided by metres squared. So we could write it as newtons per metre squared. And then hopefully we know this unit is equivalent to 1 Pascal. Alternatively, you might just know that pressure is just measured in pascals. That is the unit for pressure that we do commonly use. You might recognise that. We could also go about it by saying that we know it's not newtons per metre because it's newtons per metre squared. No, they're not going to be the same thing. And also kilograms per metre cubed we're not working with kilograms or meters cubed here, so the logical answer and the unit for pressure is going to be the Pascal. So then I can just put my final answer in the box. So we have 3,000 pascals. And then how we got the marks here. 1 mark here for substituting in the numbers, 1 mark for getting the answer of 3,000, and then the final mark for the correct unit. So here we're told that the container is put under running water from a tap and that the 3 rubber stoppers are removed. And we're told that figure 12 shows the paths taken by the water escaping from the top and bottom holes. So we've got the tap and the water flowing into the container. And then we have the top hole here, the bottom hole here, both of which have streams of water flowing out of them. And we are asked to complete figure 12 to show the path taken by the water escaping from the centre hole. So initially here I'm looking for a trend in the paths of the water. So we have at the top hole the water's falling much more closely to the base of this wooden block, and at the bottom hole it's being projected much further away from the base of the wooden block. Now this is going to be due to the difference in pressure between the pressure here at this hole and the pressure here at the top hole. So as you get deeper and deeper into a fluid, the pressure is going to increase. Now as the depth of the fluid increases, the number of particles above that point in the container is going to increase. So the weight of these particles is going to add to the pressure felt at the point, so the fluid pressure is going to increase with depth. If there's a greater force at a point, pressure is force divided by area, and that cross-sectional area is going to be the same. So with a greater force, there's going to be a greater pressure. So obviously at the bottom of the container, we're going to have a greater pressure, so the water is projected further away from the base. And then at the top here, there's less pressure, so it's projected much more closely. So following this trend, we know that halfway down the container, it's going to be projected with a pressure somewhere in between the two. The pressure is going to be between what it is at the top and bottom holes. So it's going to fall down with a path that lands between the two. And then we're asked what can be concluded from figure 12 about the pressure in a liquid. And that's basically what we've been discussing throughout the entirety of the previous question. So we've been talking about how the pressure in a liquid changes with depth. So to get the mark here, all we're going to have to write is that the pressure in a fluid is going to increase with depth. And we've seen that in the figure above, and we've explained why in the previous part of the question. Now here we're shown figure 13, which shows a simple model of a liquid. When a force pushes down on the marbles push the sides and bottom of the container outwards. So then we have figure 13. We have this plate at the top which is pushing downwards onto the marbles, and then we have the marbles sat in the container. So I'll find it useful in questions like this just to get a better sense of what we're working with, to draw some of the arrows of the forces. So if the downwards force is making the marbles push to the sides and bottom of the container, push the sides and bottom outwards, I'm just going to draw some arrows from a few different marbles. So this one's pushing to the bottom, these are pushing out to the sides, pushing out to the sides, to the bottom, just to get a better sense of what's going on here. So then we're asked what can be concluded from this model about the pressure in a liquid. So now that we've got these arrows drawn onto the model, we get a good sense of that the marbles are being pushed out. They're exerting a force on the walls and base of the containers. They're pushing a force out in all directions. Now these marbles could represent liquid particles, as we're told in the question. They represent the particles of liquid. So if we're talking about the particles in a liquid and the pressure in a liquid, we can see that the pressure in a liquid, the pressure is going to act in all directions. So it's acting out on the sides of the container, on the walls and on the base. It's going to act in all directions. We also could go about this in a slightly different way and say that the pressure causes a force on all of the surfaces. That's going to give us the mark also, pushing downwards to the side. If the marbles are exerting a force on all surfaces, there's going to be a pressure force on each surface. So, in this question, we're told that a child drops a ball and the ball hits the ground and bounces. We have figure 14, which shows the velocity time graph for the ball when the ball is dropped until when the ball reaches the top of its first bounce. And then in this case, air resistance has been ignored, so we don't have to take that into account here. We then have figure 14, so we've got velocity on the y-axis, time increasing on the x-axis, and then the motion of the ball, so between A and B, B and C, and then C and D. We're then asked to describe the motion of the ball between points A and B on figure 14. So as we can see here, between A and B, there is a straight line, increasing straight line with a constant gradient, and we can use this to work out what exactly is happening to the motion of the ball. So the gradient of a velocity time graph is going to be the acceleration of the ball. So the m, which is the gradient, is equal to the acceleration. And we know this, if we didn't know this already, we could work this out because we have the gradient of a graph is equal to the change in the y-axis over the change in the x-axis. And the y-axis is velocity, which is measured in meters per second. So if we work with the units, that's going to be a unit in meters per second. And we're dividing it by the x-axis, which is time in seconds. So the units there are the second. And that's going to give us a gradient which has units of meters per second squared, which is the unit for acceleration. So we can see here that between A and B, there's a straight line, which means the acceleration is going to be the same no matter where you are between A and B. So that means we've got this constant acceleration. And the way that we described this constant increase in velocity is going to be with the term uniform acceleration. So just by stating that there's a uniform acceleration due to this straight line, and this line, the gradient of the line is the acceleration of the ball, we're going to get both marks here for simply stating the words uniform acceleration. We'd also gain them for saying there's a constant or steady acceleration, or that velocity is increasing at a constant rate, but this is the best way to go about getting both of the marks with not too much working out. And here we're being asked what direction is the ball moving between points C and D on figure 14. So to go about doing this, I'm going to have to work out in which direction velocity is positive and which direction it's negative. So we need to work out, as the C to D portion of the gradient has a negative velocity, so it's below this x-axis, we need to work out whether the ball has a negative velocity when it's falling downwards or if it's going upwards. So we're told in the question that the ball is dropped. So if the ball is at some point away from the floor and it's dropped downwards, and then it will bounce back up. So it firstly is travelling downwards. So in the portion between the graph A and B, this ball is going to be on its descent to the floor. It's being dropped. And then the point when it hits the floor, it's going to have a velocity of 0. And then it's going to come upwards with an initial velocity here between C and D. So when it's going downwards, that's this portion of the graph between A and B, and it has a positive velocity. So the downwards direction of the ball has a positive velocity. And then when it's going upwards, it's going to obviously have the opposite. We can see this as the velocity is negative between the C and D portion of the graph. So the question is asking what direction is the ball moving between points C and D. And then we've seen on the little diagram here that it's going to be coming back up from the ground. So the answer is going to be upwards. Here we're told the ball and the earth form a system, and we're asked what's meant by a system and ticks one of the below boxes. So firstly, we have the option a group of objects that interact, and the ball and the earth do interact. These are two objects that are going to be interacting in this reaction. And then we have objects with big differences in mass. They do have a big difference in mass, however, this isn't a required criteria for them to be in a system together. We finally have objects with gravitational potential energy, and that could be a component of the system. A system could involve energy transfers and that kind of thing, but this isn't the defining feature of a system. The defining feature of a system is that we have a group of objects that are going to be interacting together. Now this could be through energy stores, through that kind of thing, through the transfer of energy, or it could be in different ways. There are lots of different ways groups of objects can interact, and this is the main thing that defines them as a system, and the earth and the ball are going to be a system in this instance. Now we're asked, when the ball hits the ground, energy is transferred from the ball to the earth. And we're asked to explain how the data in figure 14 shows this energy transfer. So initially here I've realised that this question's worth 4 marks, and it's asked us to explain how the data in figure 14 shows this energy transfer. So it's looking for a bit more information, a bit more detail, and 4 key explained points here. So, first of all, I'm just going to work out where the energy is transferred in this interaction. So, when the ball's held above the ground initially, it's going to have energy all stored in its gravitational potential store. It's not moving, so it's not got any kinetic energy, and it's being suspended above the surface of the earth, so all of its energy is going to be in this GPE store. As soon as it's released, this gravitational potential energy is converted into its kinetic energy. As it descends towards the earth, it's going to speed up as it falls. So this gravitational potential is converted into kinetic energy, and then as soon as it hits the surface of the earth, it's going to have a GPE of 0 because it's no longer suspended above the earth, but it's going to have a greater kinetic energy because this energy has been converted. However, then, energy is going to be transferred from the ball to the earth in this part of the interaction. So then the ball's going to bounce up. However, this time it's going to have less kinetic energy due to this loss in kinetic energy to the earth. And that means that it's not going to have the same GPE when it reaches the highest point in its bounce. So that's going to link in nicely to the first part of the answer. As we can see using the graph here, we have the magnitude of the velocity of the ball just before its first bounce. So here that's going to be 7. Just before it hits the ground, its velocity has a magnitude of 7. And then we have the magnitude of the velocity directly after the bounce. It's going to be -5, so it has a magnitude of 5 meters per second. So as we can see, it's gone from the original 7 down to 5 meters per second. So the velocity just after the bounce is less than just before the bounce. Now that's because of this loss, this conversion of energy and some being transferred to the earth. So that means that if it's got less kinetic energy afterwards, the height at the top of the bounce is also going to be less than the height from which it was dropped. So either of these 2 points are what we need to say to get the first mark. They're going to basically mean the same thing, just saying them in different ways. So we're going to have to write one of these down in order to gain that first mark. We're then going to go on and explain in a bit more detail what's happened. So because this velocity is less after than before the bounce, the ball must have lost energy. It's lost kinetic energy, so has a reduced gravitational potential energy after the bounce. And these 2 points here are going to get us those second 2 marks. So that the ball has lost energy will get us 1 mark, and then referencing this loss of kinetic energy or this reduced end gravitational potential energy will get us the 3rd mark. And then finally, to get the last mark here, we're going to link back to the previous question. So we know that the ball and the earth are a system. So in order to explain this a bit further, we're going to say that the total energy of the ball and the earth is going to be constant. So this energy is conserved between the two. And so just by going through this question in that logical order, we've been able to outline each mark point as we've gone and made sure we haven't missed any key information out. And explaining the question has been really important here as the command word in the question. We've had to give a little bit more detail and develop our answer a bit more. So in this question, we're told that a student carried out an investigation to determine the spring constant of a spring, and then we have table 4, which gives us the data obtained by the student. So in the left-hand column, we have the force in newtons, which from this kind of spring constant experiment that we've probably done before at GCSE, we're going to realise that this force is going to be the force applied to the spring. And then the extension of the spring, which is measured in centimetres in the right-hand column, is going to be how much the spring has extended from its equilibrium, its rest position, under the force in the left-hand column. So we're asked to describe a method the student could use to obtain the data given in Table 4. And we're told that our answer should include any cause of inaccuracy in the data, and it may include a labelled diagram. Now, obviously, I'm noticing here that this question is worth 6 marks, so it's going to be requiring quite a detailed explanation and development of the points and a good logical method with these inaccuracies brought up and shown in our answer. So, here we can effectively split our answer up into 2 main parts. So I'm going to start by focusing on the method itself, and then go on to this comment of this accuracy and inaccuracy elements at the end of my answer. So if here I begin by thinking about what I'm going to need in terms of apparatus, I always think that's a good place to start with kind of big mark experimental questions like this. So I'm obviously going to need the spring, and I'm going to be needing something to suspend this spring in order to allow for the extension that we see in the table. So I need to hold this spring up, and I could do this by using a clamp stand and clamping the spring above the ground on this clamp with a clamp on the clamp stand. So in order to measure this extension, I'm then going to need some kind of measuring implement. And in this case, we can see in the table that I'm working with values up to 20 centimetres. So a meter ruler would work quite well here. That would be quite an appropriate piece of apparatus to choose for this experiment. And then in order to ensure that the measurements here are going to be accurate, I'm going to clamp it in place using a second clamp, so clamping the ruler in place. And then we'll talk about how inaccuracies might come about if this isn't done properly a bit later on in the question, when I am talking through the inaccuracies in the data. I'm also going to be needing some 2 Newton weights to hang from the spring here, so we can see that the force applied goes from 0 to 2 to 4 and is going up in 2 Newton increments. So I'm going to be needing 2 Newton weights to hang from the spring, which is going to cause the extension present in the table. So once I've got this kind of diagram all set up, I can explain how I'm going to use this to go about completing the experiment with a clearer method. So once setting up the apparatus in the diagram, I can record the meter ruler reading that's level with the bottom of the spring. So this is going to be basically the equilibrium length and where we're going to take our measures of extension from. So I can then hang a 2 Newton weight from it and record the new position of the bottom of the spring, calculating the extension, so the difference between the original measurement and now this measurement. And I can then do this for every next multiple of 2 newtons, so adding a 2 Newton weight each time until I get up to this final value in the table of 10 newtons. And then I'm going to measure the extension from the initial position each time, so doing that subtraction, and that's going to give me the extensions in the right hand column. So as we can see, when there's a force of 0 newtons, there's obviously going to be an extension of 0 centimetres, because that is the position that we're calculating this extension from. So this method here that I've outlined is going to obtain all of the data in the table. So I've basically answered the first part of this question in that clear, logical way. Now I'm going to move on to any possible inaccuracies. So these will commonly arise relating to values found for the extension of the spring. So maybe here, back to the idea of the ruler being clamped, if it wasn't clamped vertically, so if there was an angle in the ruler, that would affect the measurements for extension. Or maybe if it was held instead of clamped, so this is going to really cause some greater inaccuracies because the error in holding the ruler instead of clamping it is going to be much greater. Similarly here, the position of the bottom of the spring could easily be misjudged, causing a difference in the extension readings. Or it could be incorrect due to a kind of parallax error, so not reading it from the same level each time. So all of these points would definitely introduce inaccuracies into the experiment, so it's good to mention a couple in the answer to get those 6 marks. So overall, here we've explained the method in a really logical, step-by-step way, using that detailed diagram at the start in order to aid in this explanation. And then we've gone on to add to our answer by including this section about the causes of the inaccuracies in the data here. So now in this part of the question, we're told that the student measured the extension for 5 different forces rather than just measuring the extension for one force. And we're asked to suggest why. This is just going to be worth 1 mark here. So we can just give a brief suggestion as to why we've conducted these sorts of repeats of measuring the extension for different forces applied. Now, one main reason for doing this may be in order to find any anomalies within the results, so we can discard them and come up with a more accurate value for the spring constant, perhaps by using an average of the reliable results that haven't been discarded as anomalies. So to get the mark here, I'm just going to write down that by doing these for different forces, it's going to help us to identify any anomalous results that we may have obtained, and then we can deal with these accordingly to come to a more accurate answer. So here we have figure 15, which shows some of the data which has been obtained by the student. So here on the y-axis we have the extension, which is measured in centimetres, and then on the x-axis we're going to have the force, which is in newtons. So then we're asked to complete figure 15 by plotting the missing data from table 4, and we're asked to draw the line of best fit. And then table 4 is repeated below to help us answer the question. So obviously here we can see that we have extension on the y-axis, and then extension is in this column of the graph. So this column of the graph is going to be plotted on the y-axis. And then we have force on the x-axis, so this column is going to be plotted on the x-axis. So for the first point we have 0.00, and we can see that's already plotted here. Now if we move on, we have 0.2 on the x-axis and 3.5 on the y-axis. Now that point isn't plotted on the graph. So if we go to 2 on the x-axis, and if this scale goes up to 5 here, each increment of 2 small squares is going to be a measure of 1. So I could plot that on here. So these 2 small squares we have 1. Here we have 2, 3, and so forth. So if we have the point 2, 3.5, we go along to 2 and up to where 3.5 is, which is this point here. We then have the point 4.8, which is plotted on the graph, the point 6, 12.5, also plotted, and now the point 816, which is missing from the graph. So if we go along to 8 on the x-axis and up to 16 on the y-axis, we get to the point here. And then finally, we have the point 10, 20, which is plotted on the graph here. So now if we're asked to draw a line of best fit, we're going to basically try and draw a line through all of these points. So if I go from the starting point all the way up to the ending point, and then straighten my line, try and get it as close to all of the points as possible. And that would get us both the marks for plotting the final results and drawing on the line of best fit. It doesn't have to go through all of the points, but it just has to make sure that there's an even number above and below the line and they all sit very closely to this line. And here we're asked to write down the equation that links extension, force and the spring constant. So for questions like these, I always find it helpful to basically go through and write out the symbols for each of the variables. So we have extension, which is going to be delta L in this case. Force is going to be a capital F, and then the spring constant is going to be a K. So now these symbols might be looking quite familiar, and a way of arranging these might be coming to mind. So the way that I like to remember this equation is with the word folk. So if I write it like this, the O in lowercase, so we know that it's not part of the equation, and I have F is equal to basically L K. And that is basically the equation here, not the exact form that we're going to write it in, but it's pretty much how we're going to work with it. So I have here that the force is going to be equal to the spring constant, so K. And then we're going to multiply that spring constant by L here, which in fact should be delta L. So that's going to be the extension. So the equation is the force is equal to the spring constant multiplied by the extension, or F equals K delta L in its more common form. So here I'm asked to calculate the spring constant of the spring that the student used and to give my answer in newtons per metre. This is important to remember that I need to give my answer in this form, so I'm just going to jot down the units next to it just so they stand out and I make sure to remember to do any conversions that might be necessary. So this question is worth 4 marks, so it's going to be important to do some rearranging and working with the equation in this question and then linking back to these units and doing any conversions necessary. So I'm going to start off here with the equation that we had in the previous question. So we worked out that F, the force, is equal to the K, spring constant, multiplied by delta L, which is the extension. Sometimes delta L might just be written as E, but either way, that's going to work just fine. So now I can basically substitute in my values from the previous question. Now if I take any of the values, this is going to work because we have a straight line of best fit. But on a graph of force against extension, the gradient of that graph is going to be the change in y over the change in x. So that's going to be force over delta L. And then if we look back to this formula, when we divide both sides by delta L, we're going to be left with K is equal to force over delta L. So the gradient of a force extension graph is just going to be equal to the spring constant. So in this case, I'm working out the gradient of the force extension graph that we were working with before, and then that's going to give us the spring constant of the spring that graph is representing. So in that case, I'm going to take the change in force throughout the whole experiment. So the greatest force is going to be that 10 newtons that was applied. So we have the 10 newtons is equal to K, multiplied by the extension that was created with that 10 newtons, which was going to be 20 centimetres. Now I'm really noticing here that we have this unit of centimetres, which doesn't quite sit right because we want our answer in newtons per metre. So in this case, I'm going to convert 20 centimetres into metres, and I'm going to do that by multiplying by 10 to the minus 3, or dividing by 1,000, whichever way you want to think about that. And that's going to give me 0.20 metres. So now I have that 10 newtons is equal to 0.20 metres times k. So if we divide both sides by 0.2 metres, we have 10 newtons divided by 0.20 metres. And if we put that into our calculators, that's going to give us a value of k of 50. So then I can just check the units here. We have newtons divided by metres, so that's going to be newtons per metre, which is, of course, the unit that we're looking for this question. So our conversions have worked, and the answer for the spring constant is going to be 50. So then the marks here are distributed like so. So firstly, for converting the centimetres into metres, and then substituting our values into the equation, doing the division to find k, and then calculating the correct value of k, which is 50. Now we're told that Hooke's law states that the extension of an elastic object is directly proportional to the force applied, provided the limit of proportionality is not exceeded. We're told that the student concluded that over the range of forces used, the spring obeyed Hooke's law. And we're asked to explain how the data supports the student's conclusion. And then this question is going to be worth 2 marks here. So we're just going to state our point and then go a little bit further into it to give a bit more detail into the explanation. So the key words that I'm focusing on here are the fact that for an object to obey Hooke's law, the graph of force against extension is going to be directly proportional. Now, directly proportional, for 2 variables to be directly proportional, they must produce a graph that goes through the origin and is a straight line. Now, if we link back to the graph that we just drew, we know that this is in fact the case for the spring. So if the spring created a straight line on a force extension graph, which also went through the origin, it's going to be creating this directly proportional graph between force and extension, showing that it is obeying Hooke's law up to this maximum force of 10 newtons that we applied. So in order to get the marks here, I'm simply going to write that the line is straight. It's going to get us the first mark. So any curve in the line would mean that the 2 variables aren't directly proportional. And then in order to get the second mark, we just need to state that it also passes through the origin, so the point 0, 0, which we can see on our graph that it in fact does. And these are the 2 criteria to basically, for 2 variables to be directly proportional to one another. This first part of the question should only be assessed on the higher tier paper, not the foundation one, but we're going to have a look through it anyway and just see how exactly we would go about answering it. So here we're told that we have P waves and S waves, and they're 2 types of seismic wave which are caused by earthquakes. And we're asked which one of the statements about P waves and S waves is correct, and to tick one of the boxes here. So we're going to tick one box and gain 1 mark for ticking the correct box. So if I just read through them to start with, we have that both of them are transverse, both of them are longitudinal, and then we have either that P waves are transverse and S waves are longitudinal, or the other way around, so P waves are longitudinal and S waves are transverse. So this is kind of quite a information recall type question. We're just looking to remember which type of wave the P and S waves are. An easy way that I like to do this is I remember that S waves, so transverse has an S, well actually it has 2 S's in it, and that reminds me that S waves are going to be transverse. Also, if you draw an S on its side, a few S's, you're going to get a wave somewhat like this, and that's also how we often represent a transverse wave. So that's often how I remember that S waves are transverse. For P waves, I often remember that P and S waves are different, and that just helps remind me that P waves are going to be longitudinal. Also, the long kind of stem part of the P is long as a long straight line, and that often helps me remember that they're going to be longitudinal. So then if I look back to the question and look through my options, if I have P waves being longitudinal and S waves being transverse, I'm going to tick option 4. So here I'm told that seismometers on the Earth's surface record the vibrations caused by seismic waves. And we have figure 16, which shows the vibration recorded by a seismometer for 1 P wave. So we have figure 16 below. This is the 1 P wave, and it has a time period of 10 seconds. And we're asked to calculate the frequency of the P wave shown in figure 16. So initially here I'm thinking about the frequency. We're working with the frequency which has the unit of hertz, which is equivalent to per second. And the definition for frequency is going to be defined as the number of waves that are going to pass a fixed point. It's important that this point remains the same each second. And this per second part is also very important, and that links back to this unit we have here. So in a period of 10 seconds, we need to work out how many waves we have shown above in the diagram. So how many complete waves are shown in this diagram. So if we're starting at this point in the wave cycle, we have to trace through a complete wave and get back to the same point. And we have 1 wave here. By doing the same principle, through a complete wave, we get back to this point for the second complete wave, and the third point here, and then finally finishes here. So we have 1, 2, 3, 4 complete waves to pass a fixed point in 10 seconds. So now if we want to work out the number of waves to pass a point in 1 second, which is going to be the frequency, we're going to have to scale this by a factor of 10. So if we have 4 waves is equal to 10 seconds, we divide both sides by 10. In 1 second, we're going to have 4 divided by 10. So that's going to give us an answer of 0.4. And that's going to be 0.4 waves per second. So that's going to be in the units of hertz or per second, and it's going to give us a frequency of 0.4. So in this question, I'm asked to write down the equation which is going to link the following variables, so frequency, wavelength and wave speed. The command words here are write down, and the question's worth 1 mark, so I simply need to state the equation here to get this mark. This question type is quite common at GCSE, so I always tend to go about this in a similar way. So I'm going to start by writing down the letters that can be used to represent each variable. So in this case we have frequency, which can be represented by a lowercase f, wavelength, which is lambda, and wave speed, which is lowercase v for velocity. And this often helps me remember the symbol equation for the 3 variables much more easily. So I remember that v is going to be equal to f lambda. Now I can just check this using the units, just check that they work out correctly in this sense. So velocity is measured in meters per second, and that should be equal to the units for frequency, which are hertz, which equates to a unit of per second, multiplied by the unit for wavelength, which is always going to be meters, and that is going to equal meters per second when they're multiplied together, so that checks out with the units for velocity. So then I can simply write this equation down using the exact terms I've used in the question. So velocity is equal to wavelength multiplied by frequency. And that will gain us the mark here. So here I'm told that the P wave shown in figure 16 is travelling 7,200 metres per second, and I'm asked to calculate the wavelength of the P wave. And I can see that this question is worth 3 marks, so I'm going to be looking to show all of my work in along the way to make sure I pick up all of these marks throughout the question. Now I can tell here if I'm working with the wavelength, so lambda, and the speed in which it's travelling, which is v for velocity. I'm going to be working with the equation that I've just written in the previous part of this question, which is going to be that wave speed is equal to the frequency multiplied by the wavelength, so v equals f lambda. So I can start by substituting in my values. We have the velocity up here, which is 7,200 metres per second. That's going to be equal to the frequency, which is going to be the frequency that we calculated in the previous part of the question and came to an answer of 0.4 Hertz, multiplied by the wavelength, which is the variable we're trying to work out here. Now, in order to calculate the wavelength, we need to divide both sides by 0.4. And that's going to leave us with the wavelength is equal to 7,200 divided by 0.4. And if we put this into our calculators, this gives us an answer of 18,000, which I can substitute into the box here. Now we're already given the unit metres, so it's a good idea just to go back and check that we didn't need to do any type of conversion throughout this question. So if we look at the formula here, we had the 7,200, which was in metres per second, divided by 0.4 Hertz, and an alternative unit for Hertz is just per second. So then these cancel out, leaving us with a unit of metres, which is what we've got at the bottom here. So we get each of our marks for firstly substituting the values in, doing the division, and then coming to the final correct answer at the end here. So this part of the question is also going to only be assessed on the higher tier paper, but again, we're going to have a look through it and see what answer we'd come up with for this question. I'm now asked to explain why the study of seismic waves provides evidence for the structure of the Earth's core. And this question's worth 2 marks, so I'm just going to make sure that I outline 2 main points here. So seismic waves are produced by earthquakes and explosions and things like that, and it's going to produce a seismic wave set of a range of frequencies which travel out through the earth and then can be detected all over the surface using seismometers. So we can use seismometers, we can put them around the earth to take in lots of data about these seismic waves, and we can analyse all of this data and detect the waves and work out a lot more about the structure of the Earth's core. So the example that we're going to focus on here for this question is the liquid nature of the Earth's core and the fact that S waves can't travel through a liquid. And this can be picked up by detections by seismometers around the Earth, and this data can be interpreted to show that the Earth's core must be liquid, which we know and think it is, and that can be shown by the fact that S waves don't pass through the Earth's core and they're unable to pass through a liquid. So to get both of the marks here, I'm firstly going to say that S waves do not travel through liquids, S waves cannot travel through a liquid, and then I'm going to go on to say that S waves do not travel through the Earth's outer core. Here, we don't have to include the word outer, but the outer core is going to be liquid and the inner core, however, isn't going to be, so it is a good idea to just make this link here also.